All right, so in this note guide over 2D momentum, we're just going to do a problem for conservation of momentum and talk about some of the concepts that apply to two dimensions. And what we're going to see is that not only is momentum conserved in a collision, but momentum in the x direction is conserved and can be thought of independently from momentum in the y direction. And that's nice. So when we write our momentum conservation, we can write it for just the x direction and just the y direction to solve the problem. So in this problem, it says a peregrine. There's an R missing there in that before the I. A peregrine falcon often grab. Peregrine falcons often grab their prey from above, while both falcon and prey are in flight. A falcon flying at 18 meters per second swoops down at a 45-degree angle from behind a pigeon flying horizontally at 9 meters per second. The falcon has a mass of 0.8 kilograms and the pigeon 0.36 kilograms. What are the speed and direction of the falcon now holding the pigeon after impact? Okay, so let's go ahead and draw this, or try to draw it. Okay, let's see here. So I'll try to draw a pigeon. And this pigeon is flying to the left, we'll say, with a initial velocity. We'll call this pigeon object 1. So we'll just call this VI1. And then the falcon swoops down from behind the pigeon at a 45-degree angle from above. So we're saying something like this, where this angle right here is 45 degrees. Try and draw a falcon here. No, this is going to be much better than my pigeon. All right, something like that, right? I gotta take an art class or something. Do some better drawings here. And in this angle, just so we can see a little better, a 45-degree angle is right there. Okay. All right. So and then we'll label this velocity. We'll call this VI2. So we'll call the falcon object 2 and the pigeon object 1. And what we're going to have to do is balance the momentum in each direction, in x and y. So let's go ahead and split this VI. Well, VI1 is just going to equal VIX for object 1, and that is the pigeon. Because all of the pigeon's velocity is to the left, which is in the x direction, and that's going to equal 9 meters per second, right? I probably should have labeled those. And VI2, do they tell us that? I think they do. This is equal to 18 meters per second. And so we can go ahead and say that the falcon has some of its velocity directed down and some of its velocity directed left. And we'll call this VIX, comma 2 and VIY, comma 2. And so what I'm trying to say there, and just so we're clear, that 1 is the pigeon and 2 is the Falcon. All right, so then after the Falcon has the pigeon, not a good day for the pigeon. I'm sure the pigeon will get away. And the Falcon has the pigeon, and they're flying together. All right. And we want to know what is the velocity, right? What is VF? And we want to know magnitude and direction. So we don't know what that is. We do know that the mass combined, right, of M1 plus 2 is going to equal 0.8 plus 0.36. What would that be? 1.16. And we know that M2, whoops, what did I just do? Did I just erase something? I think I just erased something. Dang it, I don't know where the undo button is. Oh well, I'm sure it wasn't that important. All right, so we'll say the mass of 2 is equal to 0.8 kilograms, and mass 1, where can I write that? Maybe down here, is equal to 0.36 kilograms. All right. So that's kind of where we're at. So balance momentum in the X and the Y direction. Hopefully everybody can see those a little bit better. I should have been zoomed in before. Balance momentum in the X direction. So we're going to start by saying here that PIX is equal to PFX. And we can go ahead then and write for object 1, which is the pigeon, right? We can write the pigeon's mass, which is 0.36 kilograms, times its x velocity, which I should have labeled with a negative sign up here because it is pointed to the left. All right, and we're going to go ahead and add that to object 2, which has a mass of 0.8 kilograms times its velocity, which also points left, which is equal to what? Well, it looks like we have here, we should probably label this. We have a right triangle, right? And therefore we have a hip, and we have an adjacent, and we have a theta, right? Okay, so we're thinking cosine for that. A 45-degree angle. We got 18 meters per second. The adjacent was the VIX. So we can go, and this is VIX for the Falcon. So this is object 2, right? Okay, so we have then VI to X, whatever you want to call it, is equal to 18 cos 45. All right, so we can go ahead and plug that in up here. And we should apply a sign here, right? Because it's pointed to the left. All right, and then we're going to set that equal to the mass combined, which I think we said was 1.16, times VFX, which we don't, and notice that even though we want VF, we have to put the X velocity in because we're balancing momentum only in the X direction right now. All right, so this is the idea in physics that you can talk about the X and Y direction independently. This is true in kinematics, and we're seeing it's also true in momentum conservation. All right, so go ahead and simplify this a little bit. So we get negative 3.24. Have these calculations already here. So as long as these numbers are good, we're all right. Save a little time. Okay, and then we can go ahead and simplify that. So that's going to be about negative 13 divided by 1.16, which ends up being VFX equals, well, that was negative 13.42 or so. Anyways, VFX is equal to negative 11.57 meters per second. And so that makes sense, right? If both have momentum that points to the left initially, then they will both have momentum that points to the left finally, because the momentum is conserved in the x direction. So that's what we're seeing here, is that both objects are moving together with a velocity that points to the left at negative 11.57 meters per second. All right, so we'll hold that for later. I don't know if that worked really well. Let's see if I can erase that. I like the yellow highlighter better. I think that is a little bit better. All right. Okay, so let's go ahead and balance the y momentum now. Do the exact same thing we just did. Once again, object 1 is the pigeon. And you might say, well, the pigeon was just flying left, wasn't flying up or down in the y direction, and you're right, so that's 0. So we didn't even have to really do that calculation, but I wanted to do it just because. And then we have the momentum of the falcon, peregrine falcon. This is going to be downward, which we'll call negative. Why not, right? I guess we could have called left positive and down positive as well, and not had to worry about these negative signs, but that's something's worth specifying whenever you do a problem, right? That we are calling down, not positive, down negative and up positive, and we're calling left negative and right positive. It doesn't have to be that way, but that's what we're doing for this problem. Okay, so coming back to this, we can say negative 18 meters per second. And this is going to be sine 45. Why? Because the same logic as before, right? Except now we want to know VIY2, which is an opposite. So we're just going to use theta and the hip, and once again do the same thing we did last time. Sine theta equals op over hip. Sine 45 is equal to VI2Y over 18. We can then say that VI2Y is equal to 18 meters per second sine 45. All right, so we'll go ahead. We have that right there, and we have it also being negative because we called down negative. Then we're going to go ahead and set it equal to, just like we did before, the mass of both the falcon and the pigeon times VFY. And all right, so let's go ahead and solve. So we can go ahead and say that this is just going to be 0, right? And we're going to be left with whatever this is, which is apparently negative 10.18 kg meters per second. And And then we'll divide both sides by 1.16. And we come away with VFY is equal to negative 8.78 meters per second. All right, good. Then it says solve for the total final velocity and direction using Pythagorean theorem and inverse tan. Okay, so what we're saying then is that this final direction is both left and down, right? So we know it's going to look like this for the final velocity. And we also know that it's made up of two vectors, right? A downward vector, which is negative 8.78 meters per second, and a leftward vector, which is negative 11.57 meters per second. I mean, technically, I really don't need the negative signs on these, right? Because the fact that they're pointing down and left is what the negative is saying, right? Negative indicates direction. So what we're going to do then is use, how do I want to solve for this? I kind of wanted to do down from left. So I think I'm going to rewrite this. Yeah, I don't think I want left from down. And that's what I would get right now, right? Like if I solve this right now, I would get left from down. Well, let's go ahead and solve it, and then we can always write it two ways, right? Okay, so we'll call this theta. We always like to pick the angle that is, remember this from last year, we like to pick the angle near the base of the vector we want, right? The vector we're going to get, the total vector is this blue one right here. So we'd like to have an angle that is near the base of it to make sense of it. So we can get that angle, or we can get a different angle, which I'll show you in a second. All right, so let's find this one right now. So we're going to use inverse tan. This is a 9-degree right triangle. This is going to be the opposite. And this is going to be the adjacent. So we'll say inverse tan, right? Tan theta equals op over adjacent. We can tan inverse both sides. And if we do that, tan inverse destroys tan. And then we get tan inverse on this side of op over adjacent. And that's the formula we're going to use. See, now I'm probably going to need my calculator right now to crunch that. I think it's going to end up equaling, so I have the maths kind of sort of already done, 52.81. And that is left of straight down. Yeah, that's to the left of straight down for that angle. All right, good. If we wanted to say the other angle that I was talking about, then we could find this angle right here, and this angle would be the complement of that, right? Which would be 37.19. And that would be down from left. So you could have said, or this would also describe the blue vector. So maybe this one is, so what I'm saying is it wouldn't be theta, right? It'd be theta's complement, which maybe theta's complement is, I don't know, phi, right? So phi would equal 37.19. So you could have also described the blue vector with phi, which is equal to 37.19 down from left. All right, so now we'll just go ahead and do Pythagorean theorem here and get the magnitude. We have the direction described by either of these. Let's try this highlighter. This is probably going to be crazy. Oh, yeah. All right, and described by either of those. And so let's get the magnitude. We're saying Pythagorean theorem. And we'll just call one of these A. It doesn't matter. Notice we're not using signs here. Notice I didn't use the signs in inverse tan. I really think if you would have put -11 and -8 into that inverse tan, right? If you'd have put negative signs on this, you'd get it wrong. Well, I guess not in this case you wouldn't, because the negatives would cancel. But if you had one negative in there and it shouldn't, and you didn't need it in there, you'd get it wrong. All right, so anyways, 8.78 plus 11.57. I'm not quite sure if I have a lot of the math worked out for this, and I don't think I do, but I do have the right answer. So the right answer is that C equals 14.52 meters per second. If you're not sure how to do Pythagorean theorem, by all means, go back and work that out and confirm that that's the case. Otherwise, you can just go with it. It's the hypotenuse, and it's definitely the longest side. Definitely longer than 8.78 and 11.57. All right, so our final answer then is the speed of the Falcon plus Pigeon is, whoops, looking for my highlighter, is 14.52 meters per second at 52.81 degrees left of down, or 37.19 down from left. And that's it. So once again, balancing momentum in both the X and Y directions to solve this problem, talking about their momentum balances independently from each other to solve the problem, and then bringing it back together, combining them using Pythagorean theorem, or combining the velocities. But the idea being that the momentum in each direction can be solved for and analyzed independently of the other direction. So that's it. I'll have you do some practice problems with that to help solidify that idea, and we'll go from there. All right, have a good day.